Welcome again. So already we have completed step response for the first order RC circuit with all the conceptual approaches and how to deal with the problems related to first order RC circuit. Now moving to the next topic, that is, we have already completed 3 topics. Now it's fourth one, that is the step response of the first order RL circuit. Okay, so it will be also calculated in the similar manner what we have done in case of what RC circuit. Here I am assuming I am taking an RL circuit. I am taking a current source. Okay, this is a switch, this is parallel RL connected here, and I am taking an initial current through the inductor that is equal to I naught. Okay, this is what? This is the equivalent model of what? An inductor, including the initial conditions. So as I have taken the initial value, so I have represented here. Okay, this is what? This is the time domain model of the RL circuit. Now what when we were discussing about the RC circuit, what we have done there, we have just make its Laplace domain. So I'm going to make this equivalent into its Laplace domain. What we will do, this is step signal, so Is by S. Okay, R will be same. Okay, this one, this is what? This is initial constant value, that is I naught. Okay, so I naught by S. This one is L, so it will be SL, and this current will be IL, so this current will be also ILS. Okay, now we can further reduce this circuit in its voltage equivalent. Okay, how we will do this reduction? Let's see here. You can see here this current source and this impedance SL. This is a practical current source. It is looking like a practical current source. This can be converted into its equivalent voltage source by what? By source transformation. Okay, so this arrowhead is downward, so voltage source polarity will be positive, will be in the arrow direction. This will be positive and this will be negative. What is the value of this voltage source? That is I into R. I means this current, R means impedance, that is equal to SL. If you multiply I naught by S into SL, what we will get? I naught into L. Okay, similarly this impedance will be in series. This will be SL and this will be R. This will be what? Current source. So the time domain has been converted into Laplace domain, and this Laplace domain, this current equivalent has been converted in its voltage equivalent. Okay, now we can further reduce this circuit into, this can also be reduced into its voltage equivalent. Okay, how it can be possible? Can I apply the source transformation also here? Yes, we can apply source transformation here. Why? Because the response what we want to calculate, that is the inductor current, and that is not the part of this section. That means we have already told in source transformation you can apply source transformation only if the response is outside of the source transforming units. This can be transformed into what? Into its voltage equivalent in series with the resistor. Voltage will be this current multiplied with this resistance, Is into R divided by S. Okay, so this is the complete circuit. It's a voltage equivalent circuit. Now we are interested in finding the value of what? ILT, the total current flowing through the inductor. Okay, so if we want to calculate ILT, we have to calculate this ILS, and ILS can be written as, what is the value of ILS? This voltage plus this voltage. You can apply KVL here. If you apply KVL here, what you will get? ILS is equal to Is into R by S plus I naught into L divided by total impedance of the circuit R plus SL. So ILS can be written as what? That is Is into R by S, I naught L divided by R plus SL. Is it okay? Now if we reduce this one, what we can do? This will be multiplied here, or we can break it into two sections like this. Is into R divided by S divided by what? R plus SL plus I naught L R plus SL. Okay, This can be further reduced in the form of, the denominator must be in the form of what? S plus A. Similarly here, the denominator must be in the form of S plus A, and to make it in the form of S plus A, what we will do, take L common here, take L common here. If you take this one, what you will get, you will see ISR divided by SL, this one S plus R by L, this one L, S plus R by L. Okay, now see, the whole equation can be converted like this. Now this is the function of 1 by S bracket S plus A, and this can be what? Taking the partial fraction of this one. If you take the partial fraction, this you will come out with IS by S minus IS by this one and this one. You will get this expression by doing the partial fraction of this equation. Now taking the Laplace inverse of this one, what you will get? If I am taking the Laplace inverse of this one, I am getting what? Is by S means that is equal to Is. Okay. Similarly, Is by S plus R by L, I will get minus of Is e to the power minus T by R by L. Is it okay? So this is what? This is representing the value of what? The Laplace inverse of this one is represented at this one. Similarly, the Laplace inverse of this one is represented like this one. Okay, where L by R is what? That is known as the time constant. Okay, so L by R is the time constant. So we have got ILT is equal to Is 1 minus e to the power minus t by tau plus I naught e to the power minus t by tau. Now see, it has been discussed already that the total response in the circuit is always equal to the forced response plus natural response. Okay, and the natural response is calculated only for what? Initial conditions. That means the external applied input must be 0 to get the natural response of the network. Similarly, the forced response is calculated only due to the what? The external input supply. That means when you are calculating forced response, all the initial conditions must be what? 0. Hence we can say that the total response is always what? Forced response plus natural response. Okay, now if in this section, if I want to calculate different types of responses present in the network, then what your answer? I have defined 4 types of responses. First one is what? Steady state response. A steady state response is what? If in the whole response, if you put the value of t is infinite, whatever the value you will get, that is known as the steady state response, and this is also known as the permanent response, that is not going to die out at t is equal to infinite. So in the previous expression, if you put the value of t infinite, you will get IL infinite is equal to Is. Similarly, transient state response means what? If you put the value of t is equal to infinite in the expression, you will get the value as a 0. Okay, that response which is going to die out at its steady state, that is known as the transient response. Okay, so in the total response, whatever the responses are the function of exponential terms, that is known as what? That is the transient part. So in the previous expression, you can see here, you can see what is this one? This is function of what? E to the power minus t by tau. This is function of e to the power minus t by tau. So Is into e to the power minus t by tau and plus I naught e to the power minus t by tau, that is known as what? That is known as the transient response. Okay, so transient response is defined as I naught minus Is e to the power minus t by tau. Now if someone is asking about forced response, so already explained that forced response is always calculated only due to the supply, and supply is here what? Is. So in the previous expression, just put I naught is equal to 0, whatever the value you will get, that is known as what? Forced response, that is equal to Is 1 minus e to the power minus t by tau. Okay, similarly, if someone is asking about natural response, the natural response is always calculated only due to what? Initial condition. That means the supply must be 0, and supply is what? That is I is current source. So in the previous expression, just make I is equal to 0, you will get natural response is equal to I naught e to the power minus t by tau. So the total response can always be represented in the form of forced response, and what? In the form of what? Natural response. Okay, so if I'm going to write the equation number 2, what we have got previously, that can also be written as IL infinite plus IL 0 minus IL infinite e to the power minus t by tau. In the same manner, what we have got the result in case of what? RC circuit, VC infinite plus VC 0 minus VC infinity to the power minus t by tau. Just replace V with I, whatever the relation you will get, that is the response of a first order RL circuit. IL infinite means steady state value, this one is what? Initial value, this one is what? Tau. If you do so, ILT you will get like this for what? T greater than 0, and if t is less than 0, what the value of ILT will be known as? That is known as the initial current flowing through the inductor, that is the IL 0 minus for t less than 0. This is the final expression or general expression for a RL circuit. So similarly, exactly in case of RC circuit, we have got the same relation, but this current was written in the form of voltage. In here, this is RL circuit, and we are interested in finding the inductor current. So this expression has been represented in the form of what? Current. So everything will remain same, what we were doing in case of RC circuit, exactly in the same manner we will do here in RL circuit also. There we have discussed two cases. One is source free RL circuit or natural response, and second case was what? Forced response, and third case was what? That is the total response. So I am taking the case first. What is the case first? It is saying that source free RL circuit. Source free means there is no external input supply. That means we are interested to calculate the natural response. We know that the total response ILT is a function of what? Natural response plus what? Forced response. But if we are interested in calculation of the natural response only, this must be what? This must be 0. Okay, so forced response is only due to the supply, and this must be 0 for the calculation of what? Natural response. So I am making ILFT is equal to 0. If ILFT is equal to 0, whatever response you will get, that is known as what? Natural response. And natural response is only due to the initial condition. So you can see here, put this value is equal to 0, this value is equal to 0. This is only due to the initial condition. Whatever equation you will get, IL 0 minus into e to the power minus t by tau only. And IL 0 minus is equal to, I have taken there as a I naught. Okay, so ILN t is equal to I naught e to the power minus t by tau, or can I write this one like this? IL 0 minus e to the power minus t by tau. Okay, now current we have got. Now if you are interested in calculation of the voltage across the inductor, we know that if we know the current flowing through the inductor, we can easily calculate the voltage across the inductor, that is VL is equal to L di by dt, and IT we know that that is equal to IL 0 minus e to the power minus t by tau. Just make its differentiation, what you will get? The natural response of voltage across the what? Inductor you will get, that is I naught R e to the power minus t by tau. Is it okay? So if now I want to represent graphically the current response, current natural response, and the voltage natural response, both are what? Both are what? This one is what? Exponentially decaying component. This one is what? With the negative exponentially decaying content. Okay, so if we want to graphically represent this one, this is what? If t is equal to 0, then value will be IL 0 minus, that is equal to I naught. Then after, if t approaches from greater than 0, approaches to infinity, it is getting decreasing with time t. Okay, so graphically if I want to represent this and this, how it will look like? It will look like in the same manner what we have done in capacitors. It will look 0. What is the value? Check this one. It is 0. T is equal to 0. E to the power minus t. E to the power minus 0 means what? That is equal to 1, and that is equal to I naught. Similarly, in voltage section, if put t is equal to 0, you will get minus I naught into R. This will rise like this. This will decay like this. Okay. And the definition of time constant I have already defined. It is defined as the time taken by the natural response to reach 36.8% of what? Initial value. Okay. And theoretically, steady state occurs at t is equal to infinite, but practically it occurs at what? 5 tau. We have already discussed in case of what? RC circuits. In the same manner, the case 2 is what? If I'm interested is only in finding the forced response of the RL circuit, that means natural response must be 0, and natural response 0 means the initial conditions must be 0. So to get the forced response, all the initial conditions must be 0. So in the final expressions, make the initial conditions 0. What I will get? Will get only the forced response, and the forced response will be Is bracket 1 minus e to the power minus t by tau, where Is is what? Step input supply current, and tau is what? That is L by R, that is known as the time constant. Now the current you know. Now if someone is asking about the voltage across the inductor under this condition, that means under forced response condition, then VLT, you can easily calculate LdI by dt, and you will get Is into R e to the power minus t by tau. Similarly, if you want to represent these two responses in graphical manner, you can easily develop at t is equal to 0. What is the value? E to the power minus 0, that is equal to how much? 1. 1 minus 1, 0. This will be 0. Okay. This will be 0. This will be 0. Okay. After that, you increase the value of t. You will get like this response up to what point? At t is equal to infinite. What is this value? 0. And this will be Is. So at t is equal to infinite, the value will be what? Is. Similarly, if you draw for this t is equal to 0, what is happening? E to the power 0, that is equal to 1. Is into R. Is into R. When t approaches to infinite, it will become 0. It will become 0. That means exponentially decaying component. This is exponentially decaying component. So this is the graphical representation of current, and this is the graphical representation of what? Voltage. So these two types of responses we have discussed. One is natural response and other is what? Forced response. While calculating forced response, put natural response equal to 0. While calculating natural response, put the forced response is equal to 0. Okay. And the last one is, that is the total response, and total response we have already know. What is that? ILT will be the forced response plus what? Natural response. Similarly, VLT will be forced response plus natural response, and add it up. Both responses add it up in graphically. What you will get? You will get like this, some graphical approach, and similarly like this. For this is for what? Natural. This one is for what? For forced response. Is it okay? So this is all the responses what you can develop in case of what? First order RL circuit. So the basic expression that you have to remember, that is the basic general expression for ILT, IL infinite, in the same manner what you have done in case of what? RC circuit. Now in case of RC circuit, we have developed 5 steps to solve the problems. Similarly, in RL circuit, exactly the same steps you have to follow, but everything has been replaced with what? With the current here. Okay. So step 1 is what we have discussed there. Write down the general expression of the current flowing through the inductor, IL infinite, this one. Is it okay? For t greater than 0. If t is less than 0, that means ILT will be what? Only the initial current. Okay. Next is what we have found in case of RC circuit, VC 0 minus and VC infinite. Similarly here, what we will do in the next step, IL 0 minus and IL infinite. So IL 0 minus and IL infinite we have to evaluate. But when we were doing in case of RC circuit, then what we were doing, C is replaced with an open circuit in both conditions. But here what we will do, while calculating IL 0 minus, evaluating, it is calculated before switching, and L must be what? Short circuited. Similarly, at infinite, It is calculated at switching after making L as short circuit, and T is equal to what? That is equal to infinite. Okay. And step 3 is finding the time constant, and in case of RL circuit the time constant is what? L equivalent divided by RTH, and it is always calculated after the switching. That means T is greater than 0, and while doing the calculation of RTH, what? L has been taken as load, and while calculating the L equivalent, R has been taken as load. Okay. And while all these calculation of time constant, all the independent voltage sources must be short circuited, and all the independent current sources must be what? Open circuited. So every step is same what we have discussed in case of what? Capacitors. There the time constant was RTH into C equivalent. Here the time constant is what? L equivalent by RTH. There the voltage expression is what? VC infinite, VC 0, VC infinite is what? T by tau. Here the it will be in the form of current. And what is the fourth step? That is, put the values of step 2 and step 3 in what? In step number 1, and you will get the value of what? ILT. Is it okay? So this is the step number 4. What is the step number 5? There, in case of our circuit, what we have discussed in step number 5, if someone is interested, it is asked the response other than the inductor. That is, it is not asking about ILT or VLT, it is asking about the response in any other element except inductor. Then what should be, in case of RC circuit, what was your procedure? You have to always first calculate the VCT, ICT, then after use KVL, KCL and find the other responses. In the same manner here also, if someone is asking different response other than what? Other than the L circuit, VLT or ILT, you have to calculate what? You have to calculate the value of VLT and ILT first, then after what? You will use KVL and KCL and find the value of what? Find the value of what? The other responses that has been asked in the system. Okay. So these are the 5 steps. These are the step number 3, and these are the step number 4 and 5. Okay. So remember all these 4 steps. The steps are exactly same whatever we have discussed in case of what? RC circuit. Okay. So in next lectures we will discuss about the problems related to what? First order RL circuit, and we will do everything in the same manner what we have done in case of what? RC circuit. We will apply only these 4 to 5 steps, and we will always follow such kind of calculations to get a clear understanding of the transient analysis. Okay, so we will discuss things in the next lecture, and thank you very much.